So last time I didn't explain properly about the short exact sequence. The correction from last time is as follows. So you have mi plus 1, this mi minus 1, and so on. And fi plus 1, fi, and so on. So if all image of fi plus 1 is equal to kernel fi, then equal, okay? Then it's called exact sequence. Okay, sorry, this is a mistake I made. I think some of you guys already noticed during the lecture, so you should correct me. And furthermore, so to the example of S2, so I just consider D1 plus H0, D2, H0, S2, and 0, and H1, S2, H1, D2, plus H1, D0, and H0, S1, and so on, where I just decompose S2 as the D1 and D2, and in the middle is S1, okay? S2 I decompose northern hemisphere and southern hemisphere, and it just intersection S1. And then, so from Poisson lemma, this is Z and Z and Z and Z. And also H1, S1, H2, D1, okay, and then we know this is 0, 0, 0, and this is 0, and 0, 0. So if it is so if you start with 0 and something m to the n, since this image is 0, so therefore its kernel has to be 0, okay? Kernel 0 means this is injected, okay? This kernel now, kernel f equal to 0 means this is injected. Injected, okay? And moreover, if you have something map, this is the image is everything graphs to 0. So therefore, the kernel itself is n, okay? So therefore, image of f has to be n. So this should be surjected. So therefore, f is surjected. Okay. So therefore, since it starts from 0, and this map has to be injected. Furthermore, this has to be surjected. Okay, injected plus surjected because of this 0. So therefore, this should be 0. Okay. So this map has to be surjected because of this 0. And then also we have the injected map. So this map has to be injected. So therefore it has to be 0. I didn't explain properly because of the last time I have written down this one. This is not true. Okay, sorry. I told you wrong thing. So therefore, so if you have m, mi, so image exactly has to goes to 0. Okay. Image I plus 1 should be equal to kernel of Fi. Okay. So this is, I made a mistake. Okay, so this is Mi plus 1. So it's different from complex of the chain complex. So this is correction. And furthermore, yeah, I think that's it. Yeah. So by using the same thing, so one can show that the HQ of Sn Z is equal to Z0 otherwise. Q is equal to 0n. Okay. So that's the correction I made. And also, I didn't explain something. So if you have manifold, it's a M is the closed oriented manifold, n-dimensional manifold. So then you start with the complex. If you have a triangulation of M, then you start with the complex. Start with the top complex is the n-dimensional, and so on, and the boundary map. And if you just, sorry, I think I should mention it's connected. So closed means compact and without boundary. So this means the boundary is empty. There's no boundary. Closed means the boundary is empty. So therefore, if you pick K itself, all the complex, okay? Since there's no boundary, this has to be 0, since there's no boundary. Okay? And furthermore, so the map from 0 to Cn is just 0. Okay? So there are no image. So therefore, top form and the whole complex has to be inside the homology group. Okay? Homology group. So therefore, this is usually right this form, and this is called fundamental class. So fundamental class, for instance, S2 case. So as I mentioned here in the top is the isomorphic to Z. Okay, top homology group is isomorphic to Z. So that is spanned by fundamental class. Okay? So the whole S2, and since there is no boundary, so you can take whatever triangulation, okay? Whatever triangulation, and take boundary map. Everything is there's no boundary, so therefore 0. Okay? And since image of 0 is 0, so it's automatically the homology class. Therefore, the entire complex itself is the element of homology, and that is called fundamental class. And that spans the top homology group. If it is closed, oriented, connected, and dimensional manifold, then Hn of M of Z should be isomorphic to Z. Okay, so that's a part I missed last time. And then, so Euler class, as I mentioned briefly last time, I didn't explain dimension of homology of I, M, and R coefficient, where I is equal to 0 to infinity. Okay. So important thing is this is equal to this is the R coefficient. The subtlety will show up when you use Z. Usually, homology group of Z is the following form. So this is called free Z module. This is called torsion class. This is called torsion. Okay. This is called torsion, free Z module. So bunch of copy of Z, but there is some finite group of finite group. So the example for this torsion will show up in the homework if you do carefully. And then, so if you compute the if you try to compute the Euler characteristic, this part is give you some ambiguity. What is the dimension of this one? Okay. So therefore, if you use R coefficient, so there is no such ambiguity. Okay. You don't have such ambiguity. Everything. So HI of M R coefficient is just a bunch of copy of R. That's it. So dimension. So that if it is K copy, dimension of this one is K. So there's no ambiguity for torsion class if you use R coefficient. That's why it's easy to define the homology class with R coefficient. So therefore, give you some hint at the problem. I mean, homework problem, both 3 and 4. I didn't ask, but once you compute a homology group, it's easy to compute the Euler characteristic. So therefore, it's better to compute the Euler characteristic. Any questions?
You once mentioned that to find whether the manifold is oriented, you can use the topology group.
That's true. So, if it is good. So here I just put the oriented and closed and connected. Then top homology group is isomorphic to Z. Okay. If you omit this condition, this is no longer true. Okay. You can also see the some example in homework. So if it is unoriented, a top form has some problem because of the often has. Is it always? Let me think. Yeah, I think so. I think it's always. Always, this is indeed. If it is unoriented, closed, connected, it is 0. This becomes 0. That can be shown by covering map here. So this condition is important. So if it is oriented or unoriented, it will show up the top form. If you add information, meaning if you add a condition that closed and connected. Any other questions?
So it's the Euler characteristic with summation between n.
I mean, if higher than n, everything 0.
Oh.
Any questions so far? Okay. That's a bit. Strange. Angle is not that good. Okay, so then let me move on to the homotopy equivalence of the homotopy invariance homology group. Somehow the angle is not that good. So now we will introduce the very important notion of a homotopy invariance homotopy. Okay, so roughly speaking, the homology group is invariant under this continuous deformation, and this homotopy means somehow means roughly speaking continuous deformation. So for instance, R n mod 0 is roughly speaking can continuously deform to Sn. That can be if we take x goes to x over absolute value. So essentially, there is a hole inside of Rn is captured, okay, by continuous deformation without losing information. That's the meaning of homotopy. And then we will define homotopy more precise manner. So if you think M and N are topological space, and homotopy between F and 0 is, if you consider the map between M cross I goes to I cross M, whichever, I cross M to N. So this is a continuous map. So topological space means that you can define open or closed subset, and also you can define continuous map and so on. That's the meaning of the topological space. Then we define F0x is F0x and F1, or maybe in general FT. Then F0 is called homotopic to F1. So once you have M to N, okay, the map like this way. Then the map from bottom, so this is F and bottom and top is F1. And this is capital F. And F0 and F1 is called homotopic. And furthermore, so F M goes to N is called homotopy invariance, homotopy equivalence. Equivalence if there exists G inverse map, not inverse map, so composition F and G, so F and G is homotopic identity on this homotopic also N, M, N. So you just compose G and F. So F, G is a homotopic to identity map of N. Okay. So do you see what I mean? And so roughly speaking, so there's the M, okay, and there's the M. So there's the identity map. You can from the top components identify M, and the bottom components is mapped by F dot G, compose G, okay, F compose G, and if there exists continuous map between M cross I to M, then F dot G is homotopic to identity map. Okay? And if you replace N cross I, and this one is equal to G dot F dot G, or G dot F, and identity N. If there exists some map G, continuous map G, it has to be continuous, such that the top component is identity map and bottom component is G dot F, then this is homotopic to identity of N. Okay. If this is a situation, M and N are homotopy equivalence, and we call it this is like this way, I think. And this will become indeed the equivalence class. Okay. So this didn't use any notion. So this is homotopy equivalence. And this is identity equivalence class, means that if N and L are the homotopic, this means that the M is and L are homologic. Okay. So this is the equivalence class. So this means as follows. So this means that the if you have the map M whatever N, and then okay, I think I should write down like this way. If you have M goes to N goes to L, so there is a homotopy equivalence. Means that there is an inverse, homotopy inverse, which means I call it okay, so then F1 and G1. So if F0, F1 is homotopic to as a map from M to N, and G0 and G1 is homotopic to as a map from N to L. And there's a typo in my lecture note. No, then it's okay. Sorry. So then F0.G0 is homotopic to F1.G1. Okay. Whose map is ML. So if you compose this one and this one, or this one and this one, then they're both homotopic. Yeah. So namely, so let's see. How can I explain? What's the best way to explain? So you have M and I and N. So times I. Okay. You can just compose the F0 and F1, and then there's the L. So this means that let's see, what's the best way to explain? So here you have the G1, G0 and G1, okay? G1, so they are homotopic, so there exists some function G such that their connector N cross I is continuous map to L under G. And F0 and Fi is homotopic is that there is a cylinder N cross I, and that is mapped to N, right? Okay. By big function F. Big function F. Then you can compose F0 and G, or you can compose F1 and G. Okay. So that's what it means. But in any case, so this F1 map can be just deformed in such a way that like this way. If you map on the top, okay. So so everything. So the homotopy map, this F, is everything collapsed to the one manifold N. Okay. But however, you can just take the how to say isothermal or whatever the same time. The map can be the same time, okay? Because everything, any slice is N. So therefore, any map. So for instance, FT. F is mapped from I cross M goes to N. Can be extend the map F tilde such that the I cross M is equal to I cross M in such a way that the T X is mapped to T F T X, like this way. You can just extend. So it used to be everything goes to N. Okay? Yeah, everything goes to N. So therefore, everything collapses to the bottom N. Okay, you can, for instance. But however, this can extend by just adding another direction I, okay, such that the each slice is mapped to the same time slice or same segment, same position of the segment. So that the bottom component is mapped to bottom component, top component mapped to top component. So therefore, if you just compose F0 and G0 and refine G1, everything becomes homotopic. Okay, so this you can show. Okay. So therefore, the map their homotopic becomes equivalence relation. So example, let's consider example. So Rn is a homotopic to a point or 0. So for instance, that can be shown that the F, everything point is just canonical map. X is mapped to point. So there's a Rn. Whatever. Just schematically is just a ball. Schematically is just a ball, and the point is somewhere here. All point in Rn is just shrink to the point. This is a contraction. It's called contraction map. Okay, and another map is equal to point goes to Rn. This is just inclusion. Okay, inclusion. Do you understand? So you just put the point as origin. The point goes to origin. That's the inclusion map. Okay. Let's consider G dot so the Rn goes to R0 Rn by composing F dot G. Okay. F dot G. Is it okay? So then, so this is so this is just a Rn goes to R. This map just collapse all the point to the origin. Okay. Do you understand? The origin. Then this is homotopic to identity. This is homotopic to identity map. So that the so for instance, so this can be identified as a construct F as the I cross Rn goes to Rn such that the T x is mapped to T times x. Okay. You understand? Yeah.
The composition order of map here is not consistent with that. So if you compose the F first and the J second, then the F composed J should be identity N, I think. So you should do first F the G, then F.
Okay, so that means that the what?
I mean,
so in my case, F is equal to. Oh, sorry. So then I should write down the opposite. Sorry, thank you very much. So F dot G and G dot F. Sorry. Huh? Right? Yeah, sorry. Yeah, thank you very much. So therefore this is thank you very much. G dot F F dot G. Thank you very much. This is the concept. Sorry. Thank you. So F dot G. So G dot F is just collapsing to the origin. Okay. They're collapsing to the origin. So therefore, so here, if you look at the T equals 0, everything collapses to the origin. Okay. Multiply 0 is just collapsing origin. And when T equals 1, everything is just identity map. Okay. and they are continuously connected between them. Do you understand? So therefore, if you do the video of this map at time zero, the original point, let's consider that here is x. Okay. At time zero, you have origin here. Okay, and it just continuously connected point line here. Okay, and time 0.5 is here, and so on. Everything is connected, but the time t are just the parameters that connect from origin and origin point here. And time t go to 1, it becomes, it reaches the point. Okay. So, and also we need to show, so this is g dot f dot g is equal to point map to point. And this is definitely true, right? So you just do the inclusion map the point on the origin, and after that everything crops in the point. So therefore it's identity. This is itself is identity. Identity of point. So therefore it's homotopic. So Rn is homotopic to point. Okay. The similar thing can be done by yes. So as you can easily see, so that if you look at the word of homotopy, the dimension will change. Okay, dimension is Rn here, but the point is just 0 dimension. So if you look at the word of homotopy, so the dimension is not invariant. Okay. So furthermore, so you can just consider n plus 1 origin is the same, the homotopic to Sn. Okay. So for instance, f can be defined by, as I mentioned, 0 Sn. So x goes to x divided by x. Sn so this is an inclusion map. So f dot g is Rn plus 1. Just get rid of origin. Rn plus 1. Get rid of origin. Okay. So this one is homotopic to identity of Rn plus 1 of 0. How do you construct? So this map is indeed you just get rid of point on the origin, and there's a Sn around the origin. Okay. So this is Sn inside Rn plus 1, and everything the point here is just connect to the origin. Okay. And shrink to the point that intersect. Okay, do you understand what I mean? So point x is shrinks to x mod x. You just take absolute value. Quotient by absolute value. Okay, so therefore all the point is just a move towards the origin, or from out or from inside through move from origin. Okay, so just move radius direction only. The point is radius direction. Okay. So therefore, one can just connect. So yeah. Oh yeah. Thank you very much. and G. Thank you. My brain is not working, as you can easily see. So the homotopy F, the map from I cross R n plus 1 mod 0 to R n plus 1 mod 0 construct as follows. So T x is mapped to so this is how we construct. So here you have x, and here x over x absolute value, and this map is indeed just connect between these 2 points. And at t equals 0, you have here. I think I did it wrong. At t equals 0, you're here. Okay? And at t equals 1, you're here. And as time goes, you just move along this blue line. Okay? That's a continuous deformation. That connects identity map and G dot F. This is, and also F dot G is Sn goes to Sn, and this is identity map. Identity map of Sn. That's easy to see. And last time, so I just consider Simplicia map. Simplicia map, then this will induce the homomorphism as a group. This is the induced homomorphism. So this is the Simplicia map. Simplicia map, I just remind you that the simplex is mapped to simplex. Okay? Yeah. Last time I just used this example to explain Simplicia map. That will induce homomorphism. Homomorphism is the map between group. Okay. So if you have a group and another group G prime, homomorphism means the F G dot H is equal to FG. I mean, it's consistent with the group action. That's homomorphism. And F1 is equal to what? 1 is identity in group. So on. So that's a meaning of homomorphism. It's a group. So it's Z coefficient. So Z is group, abelian group. So therefore, the map has to be homomorphism. Okay, and then, so last time we just studied the Simplicia map induces a homomorphism under the homology group. And then the theorem, if you have oh, did I use which notation? I'm sorry, I'm just. Oh yeah, I think it's okay. Okay, so then if you have the two simplicial map, okay, and if there is a homotopy between them, then homotopy, this is homotopic, then the induced homomorphism is identical as a homomorphism. Okay, so this is the actually essentially the theorem. This is indeed a statement of in the lecture. Oh, by the way, I updated the lecture note, so you should take a look at the updated lecture note. In e-learning, CLM 8.22. 8.22. So namely as follows. So if you have the k times I is k prime, so, and then if there is the F0 and F1 is continuously deformed by under homotopy at big F, okay? If you can construct such a simplicial map, then homology of K is homology of K prime. I'm going to omit, Z. So then this means that the F0 is the same as F1 as a map. In this map is the same. That's what it means. Okay. So this means as follows. So we know that the Rn is the same as homotopic to point. Okay. Okay. And also Rn is homotopic to essentially ball Dn. Okay. Dn. Okay. So therefore, Dn can be there is a simplicial map. Simplicial map K n skeleton. Did I say, what did I say? Sigma. Yeah. So sigma is equal to A0, An, so here. So this is the simplex you can consider. This is actually, you can just have the triangulation. So essentially, disk can be approximated by the triangle, right? There's a continuous mass map. This is triangulation, the continuous map. So therefore, you can have just simplicial map like this way. To the point. Okay. So this is I, and this is sigma n. Let's go sigma n. Okay. To the point. So, yeah. Oh, sorry. I think I should like mention like this way. I think I told you wrong. I think. How should I mention? Let's see. Oh, okay. I think. Yeah. I think I should use this one. Okay. So I think. Made a mistake. How should I explain? Oh, okay. So maybe here, okay, here, you have a map between F is okay. I think Rn is point and that is mapped to inclusion map. So this is the F and G. Okay, G. That will induce. Sorry, I think I should use this one. Sorry, I think I should use this one. So here you have a map between H star, homology of Rn. So, or maybe Q. Of Z coefficient is mapped to F star, and the homology of point of Z and the G star is homology of Rn and Z. Okay? Everything homomorphism. Okay? Everything homomorphism. So you can compose F star dot G star as a homology. Okay? And that is the same as identity. Okay? Do you understand what I mean? So here in bottom everything is collapsed to the point, some point. Or maybe you can just divide a little bit more by, you can just divide this simplex by subdivision, just add. And everything collapses to the point in origin, okay? Under this F star times G star, okay? But that is, so upstairs you just show that this is homotopic to identity. So that upstairs you have just identity, okay? So therefore, F star compose G star is same as identity as a homology group. Okay? As a homology identity. So therefore, F star and G star has to be isomorphic. Okay? Do you understand what I mean? Okay, let me write that a bit more. The same thing happens if you consider the opposite case. So the H star point Z is H star of R. Yeah, maybe I should write a bit left. H star of point and Z is mapped to the G star, and the H star Rn dot Z is mapped to H star point and Z. Okay. So G star dot F star is identity as a homology group of point. I'm not going to write down It's just point. So therefore, F star and G star are just the inverse map. Inverse map. Okay? To be identity. Okay? As a homomorphism. So therefore, this means that the F star is just a map from a homology of Rn. Unfortunately, I don't have a space to write down, so I'm going to erase here. So therefore, I'm just going to write down F star is the map from homology of Rn is homology of point. Okay? Since this has an inverse map, therefore this is isomorphic as a group, since this is inverse. So therefore, H star of Rn is isomorphic to H star of point. And we know that the point of homological point is just a Z in let's go Q like this. Q, let's go Q. Everything starts Q, and Q you can just write Q equals to 0, otherwise 0. And this is Poincare lemma. Any question? So since we already showed that the Rn get rid of origin is the homotopic to S n, so therefore the homology group so in this way one can show that the if M and N are homotopy equivalence, this means that the H star of M homology group is isomorphic to H star of N homology group. Okay. Do you understand? So this means that as I mentioned, so M is mapped to N is mapped to M. Okay. This will give you isomorphism between H star of M goes to H star of N goes to H star of M. So if you just compose the inducer homomorphism, this is the same as identity. Okay? The same thing will happen. So you just goes to I just making mistake about the composition. So I just write down the arrow. So H star N, H star M, H star homology group of N. And the composition of this one is indeed identity as a homomorphism. So therefore, F star is just the inverse of G star. Okay. So therefore, this will give you isomorphism of this one. So here we just see the one example. So this is called Poincare lemma. This is called Poincare lemma. So therefore, Rn is very boring. So only whatever dimension it is, it's just if it is collapsed to the point, it's just only zero homologies non-trivial. However, as you can easily see, if you get rid of origin over there, So therefore, homology group, since from this, they are homotopic equivalence, so therefore H star, HQ of Rn plus 1 mod 0 equal to, sorry, I should use Z function. Equal to what? 0 and n, and otherwise. So that's the homology group of sphere. So therefore, once you get rid of origin, okay, so some non-trivial information will show up in nth homology. Okay, so that's the difference between Rn and Rn without origin. So homology group somehow encodes the information topology in this way. Okay. And then okay. So okay, so exercise. Simple exercise, not the homework. So given the manifold M and N, given the manifold, both manifold, and you can consider homology group. Both homology group. Let's go P. Again, I forgot to bring Escher's book, sorry. I don't know why. I remember now. So and then what is the relation between whatever the product? So this is exercise during the class. Okay. So you just consider now. You can just think about it. What is the relation between them? Or can anybody answer now, this one? Let's go K. Can anybody answer? Can you come here and then do the... Okay, so I'll give you time. Okay, so in the so we already know the Rn topology, homology of Rn, and also Sn, and also in exercise. So I'm asking to compute homology of Riemann surface sigma G and RB2 and the Klein bottle. And so on. So these are very, very simple manifold. So that it's easy to compute a homology group. But by using homotopy equivalence and also the may-arbitrary spectral sequence, not spectral sequence, exact sequence, sorry, then one can compute lots of homology group. Okay. Of lots of manifold. Okay, so, and so on. And in last time I briefly mentioned that the, so there is if there is two different triangulation, So now for then so sorry, I already erased. My goodness. So then you have, let's see. Okay. So it's independent. So homology groups that computed by homology groups that computed the two triangles are isomorphic. So what I meant is essentially K of Z is isomorphic to K prime of Z. That's what I told you. So it's the manifold is so the homology group is independent of the triangulation. So that's what I told you last time. This can be just shown by just using so-called Barycentric subdivision. I mean, given a two, I mean, how to say? For instance, the sphere, or S1 can be just approximated by this triangulation, or this triangulation, or this triangulation. Okay, S1 can be, so that's, however, one can always add something in middle, the point in middle, okay? And subdivide a simplex. Subdivide a simplex. Then one can always construct a homotopy between this one and this one. Okay? That you can easily see, right? That is called Barycentric Subdivision. So given the K, one can construct Barycentric Subdivision. So for instance, given a simplex like this way, okay. Sorry. Given two simplex, one can just divide by Barycentric subdivision by lots of small simplex. Okay, that's called Barycentric subdivision. You just put the some point in here and just draw the line. That's called Barycentric subdivision. And given K and the K prime, you can always construct. So this is called, let's call F and F0 and F1, okay? So one can always construct Barycentric subdivision K many times. So many times, so I just construct N and K prime, and it's Barycentric subdivision of M, K prime, sorry. And one can always construct a Differential map, okay, from F0 and F1. So that the so essentially one can construct, if you divide the simplex enough time, so for instance, you can do this more subdivision, for instance, like this way. Like this way. So this is the actually S2. If you subdivide, do the Barycentric subdivision many times, one can construct simplicial maps such that they are homotopic. They are homotopic. That can be shown by using. That can be easily shown. That's called simplicial approximation in theorem 8.20. And then the proof is written in Hatch's book if you want. So you can just take a look at it. So therefore, by using this homotopy equivalence between barycentric subdivision, so one can show that the manifold is a homology of manifold is independent of triangulation. Computed simplicial triangulation is independent of triangulation. That's yes. Okay. Any questions so far? Does anybody solve this problem? Does anybody solve this problem for product of the manifold? Do you need more time? Okay, let's briefly talk about cohomology in that case. Cohomology. So, given a how to say simplicial complex, one so cohomology is you can just consider given a complex you can just consider chain complex, okay? Chain complex, and you can consider I think. You can generate the dual of the dual complex, which is just map between CQ, K goes to Z in a homomorphism. So, a similar way, one can just construct CQ of K and CQ plus 1 K in such a way that the so delta, I call it delta, and now in the bottom you have, if you have, so for cohomology I use the upper subscript Q. And in homology, I just use lower subscript. And the CQ, okay. But this one, I want to give you some hint in drum cohomology, right? Yeah. So drum cohomology in homework, I already tell you how it behave in the product. So you should do the same thing for homology. Anyway, so in downstairs you have the boundary map, okay? Downstairs you have a boundary map. So it has to be compatible, okay? So given start with homomorphism F and take the boundary F, okay? So here you have a complex. Chain complex is mapped to boundary of the chain complex. Okay, and you have natural pairing because you just take a dual as a vector space or Z module, more precisely. So therefore, delta F paired with C, it should be equal to F is paired by C. Okay. That's how you define this delta. That's called boundary map. This is called boundary map. This is called boundary map. And as you can easily guess or show, you can just write down right? So you can have delta and delta, delta and delta. And previously we have the opposite direction. And subscript to lower is opposite boundary. Okay. Okay. And one can easily show delta is equal to what? 0. Okay, so therefore one can do the same thing as before. One can just define the cohomology of K is the kernel of delta divided by image of delta on precisely ZQ. So this is called cohomology group. This is called cohomology. So this is very similar to, as you can easily see, in drum complex, we did the same thing. We did the same thing. Drum complex, we did like this way. Where the instead of delta we use D. Okay. And we did the same same definition. Okay. So it's the same similar way. And we can also use here. I consider as a Z coefficient. One can also consider R coefficient. So you can use, if you use R coefficient, one can indeed show that this one is isomorphic to drum cohomology of M. If you have the triangulation. Okay, so this is called drum theorem. So this is called drum theorem. And the proof is highly non-trivial. So the construction here is very different from construction in drum. So it's non-trivial to show. It's of course it's a very similar way to construct. Okay. But upstairs you have a differential form. Here we have triangulation. Okay. And then drum theorem mentioned as a vector space, they're isomorphic. as a vector space. And the proof is written in the Morita's book, also Warner's book, by using check homology. By check homology, if you are interested, you can just take a look at it. Okay, let's take a break. Any question?
Oh.
你给自己算那边知道多少？不是那个，你做那个三角形的勾弯不是单纯负形，你的那个单纯是不一样的，批准不一样。你看那个几个例子，不，那个不是三角形，它绝对不是三角形。 因为它边缘是那个它这不是 simple 这不是，它如果这个边缘属性不是单轴分析，一非要。所以说你用的单轴分析这个画面不是这个样子，它那个不叫单轴分析，它那个叫那个德尔塔复形。这两个德尔塔复形正好是相同的，所以你可以这样做。就不是它不是同样这个链群是可换的。为什么可换我也忘了，反正这样是可换的，所以你才能够这样算是一样的。但是如果你单轴复形都叫起，算了，我只能算了。它那个东西，它N对2的时候是RP3，它N对2是RP3，然后RP3就是它那个单轴复形的时候对了，如果你用那个单轴复形做RP2，这就是这个少量是啊，不知道要多麻烦。
你要把对点给连住，然后再把所有的这些东西剔除掉。
对，只需要任何做，要是没法做的。你通过一下试一下，就你反正保证它那个。
Okay, shall we start? So that can anybody tell us what's the relation? Can anybody come here and write down the relation between them? Good. Thank you very much. I think it's correct. Maybe I have to be careful. I think this is definitely correct between R, but I think it should be correct for even Z. This is definitely true. This is definitely true. Or like this way. But this one, you need to be careful. Do you understand what? Do you know what? Sometimes it has torsion. Sometimes this one is Z2, okay? And sometimes this has Z. What does that mean? Okay? You have to be careful here.
Search the Wikipedia and it says the coefficients must be a few.
Yeah. So this one does not hold indeed. So you need to be a bit careful. So you need to use some exact sequence and so on. So this one's actually a bit difficult, and I should ask you like this way. The same problem will happen. Sorry. So the reason why this is the Z2 cross Z is indeed is a bit something weird. Something weird happened. So if you replace R, it's okay. But the same thing, so I try to explain the same thing in here. Given a cohomology, one can always pair such that so this is the well-defined. So this is R coefficient, any R coefficient, Q, okay. R is ring. Ring can be anything, C, M, Z, or R, or maybe Q sometimes. Okay. So this is well-defined. Well-defined means that here you always have ambiguity. C can take C plus some boundary of something, right? Boundary of something. And also here you can have add something, the co-boundary of something. Okay. Even if you take the pairing, essentially what you can use is just the. So let's do step by step. So this is the indeed C dot F plus therefore okay. And since F is inside homology, this is 0. So therefore, this is equal to C dot F. Okay? Therefore, it's well defined. Okay? Even if you add something, some trivial thing to homology, it's a it does not affect. So this is well defined. Well defined theory. And then, so if you use the R quotient Q, K, R quotient, this is dual is isomorphic to HQ, K, R. So the homology is dual to the cohomology. If you use R quotient. Okay? So for instance, so therefore this will give you nice pair. So for instance, I can give you some examples. So what is the so this one is what? When Q is equal to what? 0. However, we know from drum cohomology the same Poincare lemma will give you the same. Okay. So what is the generator of R in drum cohomology? Do you remember? Constant map. Okay, good. So therefore, as you can easily see, HQ of R and R quotient is dual to HQ of Rn. So let's look at another example. HQ of Sn of R is isomorphic to R and 0 when Q is equal to 0 and N. The same thing happens for Sn R. Other way. So they are dual. Okay, you can see, as you can see. But if you use, so the same. If you use Z, this is dual. It's not dual. Okay. Can you give me an example? Okay, so this is the good exercise. So exercise is one example. This is not equal. For instance, sphere and the Rn is just equivalent. Okay. If you can simply change Z, everything to Z. And as you see in the homework, R coefficient and Z coefficient sometimes different. Homology groups are different. You can see. In that situation, there's something weird happening between homology and cohomology. So yeah, it's a good exercise to think when it holds and when it doesn't hold. Okay? It's a good exercise. So therefore, so in other words, the torsion part do something bit how to say, strange or weird. I wouldn't say strange or weird, but something a bit more refined version, refined information about the topology. So if you consider the z coefficient, you always have not always. So z module as a z module, bunch of free module, but you can have some torsion part. And this torsion part will give you something a bit more refined information about the topology. Now that's you can see in the homework, problem 4. And if you consider cohomology version of this one, you will see what's going to happen. I'm not going to tell you today because it's in homework. So it's a good exercise. Okay. So in drum cohomology, so we already know. So this drum theorem that tells that the cohomology is the isomorphic drum cohomology coming from. And drum cohomology so you can have ring structure. It's drum cohomology ring with wedge product. You have cohomology HK and drum and whatever lambda H L drum, then you can just have an eta wedge lambda is also inside the drum cohomology. Okay, so therefore you can introduce the product structure. Okay, so the drum cohomology itself has a vector space structure in terms of R. Okay, it's a vector space, so you can add. You can add the element. However, if you introduce the wedge product, you have a ring structure. Multiplication and the addition will give you ring structure. The similar thing you can do for cohomology. Any ring indeed. So let's go R. So this how to say? It's called mass BB R, and then this is just usual ring R. You have to distinguish. R can be any ring. You can introduce so-called cut product in such a way that the phi in HK and psi in HL such that the phi which phi cup psi and acts on some simplex in such a way that you can just decompose okay. So you can just, the counterpart of wedge product in drum cohomology is cut product. So namely, so to define a cohomology, you need to take a dual. So if you're given a simplex, so you have to map to some ring, right? Some ring R. It can be Z or ZM or R, whatever you call it. And for instance, A0 A1 and A2. And so phi can be, for instance, H1 or more generally C1. On phi and psi C1, then you can apply C1 in this simplex. So then you just apply phi A0 A1 will give you some number in ring R. Okay. On the other hand, you can also have another simplex, and besides apply from this blue simplex. Okay. That will give you element in R. Okay. And you can multiply inside a ring. Okay. That will give you cup product. Okay. And for instance, I just give you an answer. For instance, I just give you an answer. So for instance, do you know the homology, drum homology? Sorry. Homology. I think this is not good. Okay, so the homology of CPN. Do you know this homology or homology group? In fact, CP2 is what? Another way to say CP2. CP2 is topologically what? What is the dimension of CP2? Sorry, not CP1, sorry. CP1, sorry. What is the dimension of CP1? Real dimension. 2. And topologically what? It's a surface.
R2.
Topologically this is S2. Okay. And this can be understood as the R2 plus infinity. Okay. And as I mentioned, so the it has similar structure RPN. Is last time I just consider Rn with and Rn minus 1 and the union of Rn minus 2 and dot, right? That's what I told you. So Rpn is just at the infinity, you just have another copy of Rpn minus 1. Okay. The similar thing happening here. So this one essentially is, so if you consider Cpn, you just consider Cn, and at the infinity, you have a lower dimension of Cpn minus 1. Cpn minus 1. And you can continue. And indeed, each piece, so CPN is the oriented compact manifold. So therefore, so each piece will give you indeed a homology element, called homology element. Okay. The dual of so there's always a map from CPN to the some ring R, so the R, so that this one is indeed R when Q is equal to 0 to dot 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 2 and 0. So more precisely, you can easily see that the CP1. So CP1 has the following coordinate. So in the exercise, I just give you the as you just look at the how to say complex line or complex plane inside a. So you just consider Cn plus 1 mod 0 and the equivalence class by just identification times complex number. And then so these are coordinate for CPn, and so you can just, for instance, you can restrict yourself to everything to 0, and you get the point, okay, of CPn. And if you restrict yourself all the coordinate, the other coordinate up to 2 to n to 0, you get the coordinate of CP1. Okay. So therefore, CP1. So there's an inclusion. CPn includes CP1 is CPn minus 1, CPn minus 2, and CPn minus 3. Dot 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 CP1 and CP0 or point. Okay. So if you restrict yourself the coordinate, somehow coordinate to the 0, everything is collapsed to the lower dimension CPn, and that will give you, as you mentioned, some. As I mentioned, the top form will give you always a homology class. Okay. Top hom, and as I mentioned here. If you use an R coefficient, it's dual. Homology is dual to cohomology. Therefore, each top component will give you the element in R, in cohomology even. And the sum manifold is also will give you some homology element inside a CPn. Okay. These are sum manifold inside a CPn, and that will give you R. In dimension even. Okay. So each submanifold CP, how to say, lower dimensional CPK will give you, or CPQ will give you 2Q dimensional homology element, and its dual is cohomology. And moreover, you can just take the ring structure. With this cup product, this ring is indeed equal to it becomes like this way. It's polynomial ring quotient by ideal. So this means that the polynomial R. So this means that the polynomial with the A0 plus A1 x plus dot 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 A n x to the n. So the polynomial where AI is R quotient. And this x will give you dual of these submanifolds. So x corresponds to dual to CP1, x curve corresponds to dual of CP2, and so on. So if you multiply them together, you can just multiply by using cup product. Okay, this multiplication will give you ring structure, and its multiplication will give you this higher dimensional submanifold. Okay. You can just evaluate. So for instance, this x to the k can be evaluated submanifold CPK. And at the end of the day, you can have a ring structure. That's called homology ring. Anyway, so it's a bit advanced topic, which I didn't include, but anyway, just detour a bit. Okay, so let me. So this one is indeed, so here it's called ideal. So if you have x n plus 1, you should identify this is equal to 0. That's what it means. Okay, so this is a bit advanced topic, which is not written in the lecture notes. So let's move on. So M is oriented, closed, n-dimensional manifold. Okay. So then you can have, so in the previous drum homology, we already have Poincare duality. HK drum of M of drum is isomorphic to. So this is what we have learned by Poincare duality in Hodge theory. Okay. That's what we have learned. And we can have similar thing for homology and cohomology. So for instance, given a submanifold N inside N, so this is a closed submanifold. One can assign homology element inside or k-dimensional. Okay. And then one can also always assign in such a way that the so omega can be drum cohomology, or even cohomology. You can have a natural pairing between homology and cohomology. One can assign eta inside H. So to make sense, to this integral make sense, omega has to be in which form? K form. So it's a k-dimensional submanifold. So over k-dimensional submanifold, you have to integrate over k form. Okay. So therefore, any omega is HK form. You can have wedge product. Oh, thank you. So therefore, eta has to be n minus k. You can have the eta in such that this identity holds. Okay. So this one, and this will give you, this assignment will give you isomorphism between case homology and n minus k homology. So at the end of the day, so what we have is as follows. So this is isomorphic to homology, case homology of M. and this one is isomorphic to n minus k. So this is called Poincare duality. Okay, let's look at the example. So let's consider M is a 2 torus. Okay. 2 torus, and 2 torus, what is the homology group of 2 torus? In R coefficient. So since it's connected, so Q equals 0, it's R, and top component is the, also you have a fundamental class, and you have a the torus is so there are two one homologies. So one generator is the A cycle, the other is B cycle. Okay. So if you take a boundary of this one cycle, the point minus point, but there's the same point. Okay. Therefore, it becomes 0. It's the same thing happening here. Okay? So let's look at let's look at the generator of Q H0 is homology of T2. I'm going to omit the R coefficient. Is dual to H2T2. So I just use this, I just simplify here. H0 T2 from H2 T2. So as you can see, 0 and 2 are both isomorphic to R. Okay? So R, 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 R. Okay? Do you understand what I mean? And here it's generated by point here. The homology group is just point. In 0 here, this is the generated by point. This is generated by what? Top drum homology generated by what? Huh? Second top cohomology of T2. Huh? It's cohomology, drum cohomology. Do you remember? Top form. What? So it's generated by volume form. It's generated by volume form. Okay. So as you can easily see, So the point, and this one is constant function, okay? H0 is just constant function. H2 of T2 is what? What is it called? The homology element, top homology of the T2 is the generated by fundamental class. T2 itself, it's fundamental class. So this states that the, for instance, if you start with this one, T2 divided by any form omega is the same as the T2 divided times the some constant function, times a constant function, times constant function. It's very trivial thing it mentioned. Omega can be anything. If it is volume form, there is a non-trivial answer you get. Okay. If it is exact, you get 0. Okay. But T2, the fundamental graphs is dual to constant function. That's Poincare duality means here. Okay. And for instance, if you start with the point of omega can be any function. So around the point you can only have function. Okay. You have number. Okay. You can have only number. So this is the same as constant function here. So number, some number, let's go A, is that equal to the point A which omega. Okay. Sorry, T2. So therefore, point is dual to volume form. Okay. T2, you have a volume form, and you get 1 essentially. You get the 1. Essentially, if you evaluate volume form of T2, you get 1. So the 1 times some number will give you isomorphism between the equality here. Okay. So therefore, the point is Poincare dual to volume form. Okay. So it's a very, very trivial thing I'm talking about. But now, so let's look at the H1 of T2, Poincare dual to H1 of T2, from H1 of T2, from H1 of T2. So here let's go, so as he mentioned, so let's call this one, this element is dx, and this element is dy. Okay. And dx is the volume form of this S1. Okay. And the dy is volume form blue S1. Okay. It's a circle. And then, for instance, you can just consider let's start with H1 of T2 as element of this red circle. So let's circle here. Red circle here, let's call A cycle and B cycle. Blue I think, okay, let's go like this way. If you start A cycle is the generator of H1. What is the Poincare dual? Question is. So Poincare dual A omega is equal to T2 omega with something, right? What is has to be? What is the dual? What is the dual of A? Poincare dual of A. Either dx or dy, because it's generated by dx or dy. This H1 is generated by dx and dy. Which one should come here? So it should become dy. If you get the if you omega is dx, you get non-trivial answer. You get the 1 here if you normalize appropriately. Okay? You get the 1 here because you can integrate dx along A. Okay? So you have to wedge dy. So therefore, A is Poincare to dy. And of course, by Poincare by using Hodge product, you should get the bottom form. Okay? If you take wedge product between them, you should get the bottom form. So therefore, they are Poincare to dx. Okay? And they are Poincare to B. Do you understand? Do you understand what I mean? Good. So that's how they're connected. And if you look at the A and B, they intersect at a point. Okay. So therefore, one can just define the so-called given a submanifold N1. So given a A1, A cycle and B cycle as an intersection form, intersection number. So this is called intersection number, such that the so you can generalize this notion. So this is called intersection number. So this is called intersection number. So given the sum, so in general, given a manifold, there is some manifold N1 and 2. Okay? Some manifold such that the you have element in HK. Oh, sorry, sub K. So you can just consider the intersection number as you can just take its Poincare. So take Poincare. Poincare, eta 1, eta 2. Okay. In Ramka homology. So this one is the Hn minus k Ramka homology. Hk Ramka homology. And you just take wedge product and integrate over. That will give you intersection number of some manifold. Okay, any question? Do you understand? So let's consider M and N, n-dimensional, connected, oriented, closed manifold, and you have a smooth map. Okay, and then so that will induce so-called the homology. Homomorphism between a homology group. And you can define mapping degree as star. Mapping degree. So the M and N are the n-dimensional manifold. So therefore, so you can define a fundamental class. M and N are fundamental class. And then under the what is it? How to say? Under the smooth map. So one can just define the degree. It's called mapping degree of F by using how many times essentially wrap. For instance, if you start with S1, both M and N are S1. Let's consider the case M and N is equal to S1, okay? And then consider the map F S1 cross S1 in such a way that EI Sailor to EI and Sailor, okay? Do you understand what I mean? So you have to so circle is mapped to n times like this way. Okay? Okay. So in this case, under this map, F star H1 of S1 is mapped to H1 of S1, but you have n copy of S1. So therefore, that means that the so mapping how to say S1 fundamental class of S1 is mapped to n times S1. Okay. Therefore, mapping degree F is equal to n. Okay? And as you can easily see, this is homotopic equivalence. For instance, given a circle, and you can just map whatever where. So you can go back and like this way, whatever way, right? This is at the end of the day, so it's a homotopic equivalence to twice of the to double covering. Okay, it's double covering. So homotopic equivalence means that continuously this map is deformed to the just usual double covering. Okay. Therefore, homotopic equivalence means that you can deform this red map to this blue map by continuously. So if you consider I cross S1, you can, from bottom, you just have a red map, from up, and from top, you have a blue map. And you can continuously deform. That's the meaning of homotopy. So this is mapping degree. Another way to define mapping degree is just using, here I use homology. You can do the same thing for homology by using convergility. Since this is n-dimensional connected oriented cross manifold, so mapping degree of F can be understood. Now F is actually induce the pullback in cohomology. Okay, it's a pullback. So it's a pullback. So homology is a push forward. Okay, always dual. This is the F star of omega M F star. Which one? N? Sorry, F star M? Yeah. Well, omega is volume form. Okay. Okay, so then let's consider so-called this mapping class mapping degree. First sharp Gauss to linking number. So linking number, so let's consider link. Link is S1 cross S1 inside Rn. So such a way that the whatever link is whatever. It's the simplest link is called. Do you know what is it called? What is it called? It's called Hoff link. Whatever link, another link is what? I mean, there are many links one can consider. And you can just consider some orientation, okay? So this is inside of Rn. So R3, sorry. R3, okay? R3, and then you can define a map between, so map you can define from here, so this is link. Yeah. You can define a map, I call it F, which is S1 cross S1, which is Taurus to S2, in such a way that the X1, X2 is mapped to X1 minus X2 divided by X1. So you just took X1 is here, X2. Okay, and then you just take divide by absolute value. You can just rotate on a circle. So then, if you take the absolute value, so if you take the unit length, if you take unit length, you get a map to S2. Okay, essentially. So this is map from essentially this is T2. Both are two-dimensional connected cross-oriented manifold. And you can consider the degree, so this is mapping linking number of L, such that this is degree of F. And this is equal to indeed 1/4 pi divided by T2 F star of omega. Omega is volume form of S2. So omega is volume form of S2. Essentially, how to say? Is this sign? So then, this can be written as follows. This can be written as follows. So by using volume form, so over here we already learned this one is essentially dx1, which how to say dx. Oh my goodness. Right? And the pullback of this form. You already did in homework, right? Do you remember? This is divided by, how to say, x1? X. In homework, I just give you the form inside Rn minus 1 plus 1 mod 0, which is of this form, and if you pull back this form into Sn, you get the volume form. Do you remember the homework? And then, so denominator is always 1 in this case, because it's unit circle, okay? So therefore, you can just consider, this is the volume form of, just pull back of this one, we give you volume. And if you use this one, let me check. I think I don't want to make a mistake. I already did lots of mistakes. Let me be precise in that case. So you guys should tell me. You guys already solved the problem. Yeah. Oh yeah. Yeah, clearly I made a mistake. Good. It's worth checking. Okay, clearly I made a mistake. It's worth checking. And this is not true. So another way to write this one is a pullback of the form omega is equal to 1 over x, sum of minus I, xi, dx1, which dxi, and just get rid of this one, and dxn. Yeah. So this is a form of the inside. This is the top of form of omega n or n mod t. And if you pull back this form, you will get and more precisely, this is n. Sorry. So this is n. Yeah. And if you pull back this form into the Sn minus 1, you get the bottom form Sn minus 1. That's what you already computed. And so in the three-dimensional case, omega n minus 1. Omega 2 R3 exercise, this one will become, let's see, x cube. Let's do step by step because I will always make a mistake. Okay, and let me continue to here. Everything becomes cyclic. Okay, so this is a form. Okay, do you understand? So if you restrict yourself this one, you get this one. And then one can write down this integral as follows. This integral can be written as, so linking number is 1 over 4 pi t2 f star omega, and omega is this one, okay? Inside, and this is omega, and then this can be written down 1 over 4 pi let's call this one K1 and K2. K1 x minus x1 K1 times dx1 dt1 x minus a cube. So here, so x1, so x1 is a position of here, and that is parameterized by t1, and then x is the sorry, I got confused. Oh yeah. Yeah. So yeah. So this is S2, the volume from back to here. Oh, sorry. That's why. Sorry. I'm sorry. So this is not precise, sorry. Yeah, this is the correct form. Okay, so as you can easily see, yeah. So if you pull back this volume form by this map F, so you can just have the integration over K1 and K2 of this one. And it turns out that if you consider the current, so you have a electric current undergoes running under this K1, it will generate a magnetic flux, okay, by Biot-Savart theorem. So as you can see, so you have a electric current running along this K1. It generates the magnetic flux, a magnetic field, like this way by Biot-Savart theorem, right? That's what you have learned in the electromagnetism. And this magnetic field B is indeed given by x minus x1t divided by x minus the position at the x, sorry, x1t, oh gosh, times dx1 dt. So this is the magnetic flux generated by the current. Therefore, this integral is indeed, you just put the magnetic monopole here and move along another circle, and how much energy it costs. Okay? That's how the linking number will tell us. So the linking number here is indeed the energy that cost in order to move the magnetic monopole along one linking component when the unit current electric current undergoes the other component of the link. So and indeed, so this is indeed the invariant up to the formation. So whatever circle you take, linking number doesn't change. Okay? So even though magnetic flux at this point is different from this point, so you can continuously form the circle, but at the end of the day, so linking number should be the same. Okay. So that's how we obtained the linking number. Unfortunately, I didn't get to the end. Sorry. Yes. Thank you very much. Thank you very much. So, oh my goodness, lots of mistakes, K1 and dt1, and also there's an overall coefficient. Yeah, this is magnetic flux. Okay. So therefore, this component is just a B flux, and just integrate over will give you energy. Okay, so let's stop here.